Hello, mathematicians, puzzlers, and other curious people. This is a follow-up post to something I posted last month about square numbers. So you probably remember. If not, please jump back and familiarize yourself with this. But you probably remember that square numbers are numbers that can be sort of nicely drawn as squares, with an integer amount of length on each side. So you could have 1 by 1, 2 by 2, 3 by 3, etc. And I suggested that that would be a good topic to investigate in different ways. I posted some starter questions, and I'm definitely not going to answer all of these questions today, but I had one in particular I wanted to look at. So, what happens when you, in particular, multiply a pair of square numbers? So, that's going to be maybe one of the easier ones to investigate, pretty straightforward, but it can definitely still be interesting, and it shows some ideas about how we investigate things to do with numbers. So let's take a look at how we will investigate this topic. So I'm going to use random.org to generate some random integers. So I'm going to generate 10 random integers. I'm setting it to have each integer having a value between 1 and 20, and to give me that list in 2 columns. Okay, so here's what that gave me. So I'm going to start with the first pair, 2 and 15. Whoops, okay, good, it's working. Okay, 2 and 15. Their squares would be 4, because 2 times 2 is 4, and then 15 times 15. Let's see, 15 times 15. So 100, 50 and 50 would be another 100, so 225. 4 and 225. Okay, very different numbers here, right? So clearly their product would be 229. Or wait, no, sorry, that's their sum. My bad. So 4 times 225. That's not a convenient one to do mentally. So let's see, that's going to be 880 and 20. So that should be 900. Okay. So 900 might be an interesting number. Let's see what else this has in common. So let's see, I notice it's a multiple of 100. I notice it's a multiple of 9, therefore a multiple of 3. I notice it's a multiple of 10. It's even. It's a multiple of 5. Okay, 8 and 4. Let's see what we get from that. So let's see. 8 and 4. 8 times 8 is 64. 4 times 4 is 16. Let's see, 64 times 16. This is convenient because these are both members of that doubling sequence. So let's see, 64 would be 2, 4, 8, 16. Okay, so that's going to be the fourth member of the doubling sequence. Okay, 32, 64, the sixth member. Well, that would give us the 10th member of the doubling sequence, which is 1024. I promise I am not making it give me nice numbers on purpose. So I notice that this is not a multiple of 100. So not always, only sometimes. I notice it's not a multiple of 10. So not always, only sometimes. I notice it is even. Let's see. Other things we could notice about it. Oh, but I noticed that 900 was not a member of the doubling sequence. Whoops, sequence. So again, that's not always, only sometimes, because 900 wasn't. So that's great. We're generating hypotheses and we're finding counterexamples for some of them. That helps us narrow down which hypotheses are worth trying to find a proof for. Let's see. 4 times 10, okay. Or sorry, 4 and 10, my bad. Let's see, 4 and 10 as our pair of starter integers. Let's see, 4 squared is 16. We just used that one. Cool. Okay, 16, 10 times 10 is 100. 16 times 100 would be 1,600. So let's see, it's even. So are they always even? That would be interesting. Well, my next pair of random numbers is 1 and 11. So let's see, 1 and 11. Well, 1 times 1 is 1. 11 times 11 is 121. I've memorized that from using it many times, is how I know that right away. And then 1 times anything is the thing. So 1 times 121 is 121, which is not even. So these are not always even, only sometimes. I notice here that we started with 2 odd numbers. And I notice here that each of our other pairs of numbers had at least 1, sometimes 2 even numbers in it. So maybe that is why the product of those square numbers came out even. And then this one came out odd because the roots of the squares were both odd. That could be something to investigate as to whether there's a pattern between how it's determined to be even or odd. Okay, so we know it's not always even. We know it's not always a multiple of 10, let alone 100. Here's something I noticed, though. I noticed that 1600 is kind of an interesting number because it's the same as 40 times 40. So that product of square numbers is itself another square number. A 1,024, well, that's a little bit trickier. But it turns out that 32 times 32 is 1,024. How did I do that one, by the way? I said, okay, what if we took one of these 2's? So what we had here was 2 times 2 times 2 times 2 times 2 times 2. Okay, so that was the 2 to the 6th, and then we had a 2 to the 4th. Okay, well, what if we regrouped that to 2 to the 5th times 2 to the 5th? 900, well, 9 is easy. That has a square root of 3. And then 30 times 30 would be 900. 121 we just got right here. So it seems like it might be the case that a square number times a square number always gives us another square number. So is it true that one number squared, I'm going to call these numbers n and these numbers m just because it's right there convenient in the alphabet. So is it the case that n squared times m squared is another square number? Let's do one more to see if we get a counterexample. Okay, 17 and 8 was my next pair of randomly generated numbers. Okay, 17 and 8. I know 8 times 8 is 64. 17 times 17 isn't one I've memorized, but we can work it out. Okay, so 100 and 140, so we've got 240. 240 and 49 would be 289. Okay. So 289 times 64 see. 8 times 6 is 48. 9 times 6 is 54. 2 times 4 is 8. 4 times 8 is 32. 4 times 9 is 36. Okay, so we've got 36. Let's see. On this diagonal of things that are actually tens, 32 tens and 54 tens would be 86 tens. So really 860. On our tens times tens, or ones times hundreds, we've got 48 and 8, so that would be 56. So really 56 hundreds. And then 12, well, that's tens times hundreds, that would be thousands. So 12,000. Okay, so let's see. That is 6, 96. So really, yeah, 90, let's see. 800 and 600 would be 1400, so really 1,400. Let's see, 5,000 and another 1,000 is 6,000, and 2 more thousands is 8,000. So 18,496. Wow, okay. Big number. And I guess that's not surprising because we started with fairly large numbers. So this is going to be a little on the inconvenient side to do in any other way. So I'm going to grab my phone and I'm going to let its calculator do a little work for me, because yes, I could do this manually if I wanted to, and if that were the point of this video. But you know what? That's not even the point of this video. So I'm going to flip my calculator. I'm going to flip my phone so its calculator goes into scientific mode, and I'm going to use my square root button, and I'm going to say, okay, calculator, this is your one job right now. Tell me the square root of 18,496. My calculator tells me that that is 136. So that is a square number. So 136 times 136. Okay, so it's possible that I got lucky with everything that, with these 5 pairs of square numbers that I came up with. So again, 5 pairs of randomly generated square roots, multiplied them up into squares, multiplied those squares by each other, and got another square number. It's possible I just got lucky, but it would be a little bit weird. So let's see if we can see a reason why that has to happen. So remember, n was just a number, and m was just a number. Well, that gave me n squared and m squared, and I multiplied them together. But n squared is really just n times n. That's how I got it in the first place. And m squared was just m times m. Now, if we had, for example, and I'm going to use our fairly straightforward pair of numbers. Let's see, 2 and 15 was what we started with. So if we had 2 times 2 times 15 times 15. Well, this 2 times 15 in the middle here, I know that's 30, but that's the same as 15 times 2. So I can get the same result by multiplying in either order. So that would be the same as doing 2 times 15 times 2 times 15. Well, that's 30 and 30. So I have to get back 30 times 30, which is a square number. Oh, look, I did. Interesting. Well, this didn't only work because it was 2 and 15. Any pair of numbers, if you're multiplying them, you can multiply in whatever order is convenient. So we can interchange n and m here. So we would have n times m, copying over the rest of the problem around it, times n times m. But that just says that what we've got here is n times m times n times m, which is just n times m squared. I didn't write that over here, but that's the same as if I wrote that as 30 squared. But that's got to be a square number. So there we go. Not only does does a product of two square numbers have to be another square number? But we can just multiply together their square roots to find out its square root. So that could have been way easier than what I had to do here, and I ended up outsourcing it to the calculator. I could have just said, okay, 17 times 8. Well, that'd be 80 and 56, which is 136. Just like the calculator said it should be. Okay, so this is awesome. Anytime you multiply two square numbers, you have to get another square number. We don't need that question mark anymore. We have proven it. So try some more things out. Have fun with writing proofs, Look for patterns. Find things that you think are awesome, and see if you can find a good formula type reason. Whoops, I just realized that had not scrolled down far enough. Okay, so I hope that I made sense as I was talking through that. But yeah, see if you can find a good formula reason why it has to be the case that the cool pattern you notice has to always happen. Or, if it doesn't always have to happen, like what happened here with some of them being odd and some of them being even, see if you can find under what circumstances the product of two square numbers would be odd or even. So, like I said, though, have some fun with this. Try things, look for patterns, because that's what math is all about. That and catching your mistakes. It happens. So, for the moment, though, I'm Avrila at Math with Avrila, and I'm going to say, calc you later.